Uh, Hello everyone, I am Bhaskar De and today is the fourth live problem solving session for the course Introduction to Laser. So in the last class I have discussed about the spectroscopic term symbols. So in the course by now you have seen the application of this term symbol for NDI laser. So now with reference to the last week's videos, uh, this week's videos, I will just discuss about the Nd+3 ion. So number of electron 57, and if I write the electronic configuration, one s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 5s2 5p6 4f3. So this is the electronic configuration. Now for 4f there are 7 boxes. Now there are 3 electrons. So this one, so 3 electron goes here, so it is like this. Now the term symbol, so the term symbol is 2s plus 1 Lj. So here total spin angular momentum is equal to half plus half plus half. 3 by 2. Now there are 3 electrons, that is L1, so this is plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. So L1 equal to 3, L2 equal to 2, and L3 equal to 1. So now capital L equal to summation I Li equal to 3 plus 2 plus 1 equal to 6. Now I have already calculated the value of S here, so multiplicity two S plus 1 equal to 2 into 3 by 2 plus 1, 4. Okay, so now we need to find out J. So J equal to L minus S, that is but there are possibility of J, so value of J can be L minus S to L plus S. So then it will be 6 minus 3 by 2 to 6 plus 3 by 2. So it is 9 by 2 to 15 by 2. So the value of J will be 9 by 2, 11 by 2, 13 by 2, and 15 by 2. Okay, now L equal to 6. So as I have mentioned in the last class, if capital L equal to 6, then the term symbol will be S P D F G H I. So here it is as the value of L equal to 6, so it will be this one. So the term symbol for the ground state splitting will be, after LS coupling, is 2s plus 1 2s plus 1 Lj, that will be 4 I j. So it will be 4 I 9 by 2, 4 I 11 by 2, 4 I 13 by 2, 4 I 15 by 2. Similarly, you can calculate the spectroscopic term symbol for the excited state. So this is how the term symbol or the name of the energy states are defined for the Nd plus 3 ion. So this is the electronic configuration. From that, the last electronic configuration for the last subcell is used, where there is 3 electron in the 4f orbital, 4f subcell. So now from that I have calculated the value of total spin angular momentum S, total angular momentum L. Then from that I have calculated the multiplicity, and then I have calculated the value of J, which is L minus S to L plus S. Okay. So this was the revision based on the last week's video. Now I will proceed to today's topic. So here I am going to discuss about two things. One, properties of laser beam. Two, a method that is known as matrix method. Okay. So the first thing is properties of laser beam. So in the properties of laser beam, there are multiple things you can think of, but mainly we talk about monochromaticity, coherence, directionality, or brightness, and 5, which is not necessary for every laser, but it is one of the reasons that the development of laser is still one of the open research topic in current time, and that is short time duration. So these are the 5 things. Now first one is monochrome. So by this term, what do we mean? We mean that the laser that is emitted from the active medium or gain medium is, or the optical resonator is actually of a single wavelength. So from the transition, spontaneous emission, you have seen that there is a broadening in the transition, and that's why you cannot have a single wavelength. But by monochromaticity we mean that the line width is as less as possible. So this monochromaticity arises from two reasons. One is that only an EM wave of frequency mu naught can be amplified to 2 meter arrangement forms a resonant cavity where oscillation can occur at the resonance frequency of the cavity. So for particularly these two reasons, we have a monochromatic light beam from the laser. So but by monochromatic, I am not saying that the laser will have a particular single wavelength. It will have a central wavelength. For example, when we say that there is a laser that is of the wavelength of 730 nanometer or maybe of 660 nanometer, then that means that this is the central wavelength. But if you check this laser beam with a spectrometer, you will see that the profile of this beam are like this. Here it is 730, and when you check, you can see that this part is around 760 and here it is 700. So it is around uh, 60 nanometer. So that means that the line width is around 60 nanometer, but the most dominant one is this one, that is the 730 nanometer. But depending on the size of the resonant cavity, this 60 nanometer can be narrowed down to some nanometers. Some nanometer means that 1 to 10 nanometer. So this thing will become 730. Here it is 735 and here it is 725. Okay, so this is one of the property, that is the monochromaticity. Then there is coherence. So this one I will not discuss today properly because I have already discussed this in one of the problem solving session where I have mentioned about two coherence particularly. That is, one is the temporal coherence and another is the spatial coherence. So by temporal coherence, what we mean is that the phase of the EM wave is same or relatively same at t and t plus t. So at 2 point of time the phase will be same, and in the second spatial coherence the phase difference at 2 points of the EM wave is constant with time. So basically one is constant in time, this one is for time, and this one is for space. So a EM wave is traveling from x0 to x1, and the phase is like from the phase here and the phase here, here the phase difference between these two points is constant over time. It is constant over t equal to 0 to t equal to capital T, and this is the spatial coherence. And the temporal coherence is that the phase here is constant throughout the time t equal to 0 to t equal to t. So for spatial coherence the phase difference needs to be constant, but for temporal coherence the phase should be constant over time. Any doubt till now? You can unmute yourself and ask if you have any doubt.
No, sir.
Okay. So at this point one major thing I need to point out that this spatial and temporal coherence are independent spatial and temporal coherence are independent of each other. So this means that the beam can be temporally coherent in time. So by coherent in time means that the phase at x0 is same as the phase as x0 at t equal to capital T. So over time the phase at x0 is constant. Okay, and again, but that should not mean that the spatial coherence will be there. Like the phase difference may not be constant over time. This phase difference may not be constant over time. So that is, there is a temporal coherence, but there is no the spatial coherence is not there. Again, it can happen that the phase is changing constantly at x0 and x1, but the phase difference delta phi is not changing. That means that there is a spatial coherence, but there is no temporal coherence in the beam. So these two coherence are independent of each other. Now the third property of a laser beam is directionality. Directionality is a direct consequence that the active medium is placed in a resonant cavity. So from the resonant cavity the beam emits in a particular direction. So the directionality is basically measured by the divergence of a so directionality is measured by the divergence of a plane EM wave due to diffraction. So now the laser beams, so this is the laser beam coming with a plane wavefront. Then there is a aperture that has a diameter of uh, d. Then after the diffraction from this aperture, it will diverge a little bit, and there is this skin. So by the definition of diffraction, you know that if there is a plane EM wave incident on a small aperture, it will diverge, and the wavefront will, these are the wavefront of the laser beam, that is plane or straight line. So it is looking like a straight line, but it is actually like this. This is how a plane EM wave is operating. So now if it is incident on an aperture, then from the aperture it will start to diverge, and the wavefront of a diverging beam is like this. So when there is a point source, then we see always a spherical wavefront. So when there is a tube light or something like that, then we will have a cylindrical waveform. So when there is a diffraction, then we will see this kind of spherical wavefront at the skin, and this is the divergence angle theta d. So now this theta d can be written as b lambda by d. So here lambda is the wavelength, d is the aperture size, and beta is the numerical coefficient of the order unity, whose value depends on the shape of the amplitude distribution and on the so this numerical coefficient has a order of unity. So now again this thing this is related to the spatial coherence also. So this can be rewritten in the form b lambda by sc to the power half, where this sc is known as coherence area. So this sc is so t is the aperture size and sc is the square. D is the diameter of the aperture, and then SC is the square root. SC is the coherence area, so D is basically square root of SC.
Sir, couldn't hear, sir, please.
Hello.
Sir, I couldn't hear, sir. A little bit louder, please, sir.
Oh, so from where you could not
Uh,
listen?
yes, sir.
No, I mean, did you have you got the discussion, or like you have missed some point of this discussion?
No, no, sir. Not asking the doubt, sir. I'm asking to. I'm telling you to please a little bit. Can you
Okay, okay,
increase
okay.
your?
I got it. I got it. Okay.
Thank you, sir. Thank you so much, sir.
Okay. So this is the directionality of the laser. Now then there is another property, that is the brightness. So by definition, brightness is of a given source of EMI is the power emitted per unit surface area per unit solid angle. So this is the definition of the brightness: power emitted per unit surface area per unit solid angle. So let ds be the elemental surface area let me draw the picture first. This is the surface of ds, and then from there the perpendicular is in this direction n, and this is the direction of the beam. So this is theta and this is focus. Now so this is the elemental surface area ds for the point of at point 2 of the source. Now the power emitted from this source is dp. Okay, so dp equal to So the dp power is emitted by ds into a solid angle d omega. So around the direction, around this direction o dash. So dp can be written in terms of b cos theta. The theta is this angle, the angle that is between the o dash and n is the perpendicular with the surface. So dp equal to b cos theta ds d omega. So ds is the elemental surface area, d omega is the solid angle that is made around direction o dash, and theta is the angle between the perpendicular and the direction. Now here one quantity that is unknown, that is this b. This b is known as the source brightness at point O. So when b is constant, then the source will be known as isotropic source. So this, now what is this ds? For example, if there is a bulb, the surface area of the bulb is like, so this is the bulb. So at, you can define the surface area here or here, anywhere, and if this b is constant everywhere, then for example here the b is b1, here the b is b2. If b1 and b2 is equal or constant everywhere, then we will say that this is a isotropic source. So now for laser, what we will do is that, let us consider a laser beam of power P. With a circular cross section of diameter d and with a divergence theta. So now for laser beam the directionality is very high, so theta is very small. So almost, if we calculate, the cos theta will be close to 1. So the, now the area of the beam is pi d square by 4, as d is the diameter, so it will be pi d square by 4, and the emission solid angle is pi theta square. Then according to the equation we will have p equal to b cos theta d dp ds d omega. Now here we have power p, the brightness, then cos theta equal to 1, so there will be no cos theta term. Then the surface area of the beam is pi d square by 4, and d omega is pi theta square. So from that we will have P equal to 4p by pi d theta whole square. So if the beam is diffraction limited, we will have theta equal to theta d. So this is the lowest value of theta. So we can write this as b equal to 2 by beta pi lambda whole square p. So here we have just replaced this with the earlier equation beta lambda by d. So this is when the beam is diffraction limited, this is the maximum brightness at a beam of power P can have. So now the laser beam will always have a large brightness, and it will be several order higher than a conventional light source, because this beta here is smaller for a laser rather than for a conventional light source. By conventional light source we mean some kind of lamp or something. So due to this factor beta, for diffraction limited beam, the or you can say the directionality of the laser beam is higher, so this beta is small. That's why the brightness, like if we compare a milliwatt laser milliwatt laser and a watt lamp, then both of them has a power of milliwatt, or for say it has 1 milliwatt laser and 1 milliwatt lamp. Then due to the low value of beta, the brightness of this one will be higher. Now there is another property that is optional for some laser, that is the short time duration. Mostly when we think about a electromagnetic wave or a laser beam, we draw it like this. This is a continuous electromagnetic wave traveling, but there is a different kind of electromagnetic wave or laser pulse we can have. So there are two types of laser. One is CW laser, which is known as continuous wave laser, and this laser emits the laser beam like this, a plain electromagnetic wave. Okay, and there is another thing, that is pulse laser, which gives the laser pulse like this. So all these things should be I mean equivalent, but here my drawing is not that good, so it's looking different, but these things are actually equal. So now the short time duration, for here there is no time duration for the CW laser, but when it comes to pulse laser, is it the time duration that is known as this one, that like the speciality of this pulse laser is that there is no pulse, then certainly there is a pulse, very high intensity pulse, then again there is no pulse, and then there is again a pulse, and it goes on. So now this thing, the duration where the pulse is present, is known as the pulse width. So this pulse width can be of any order, from nanosecond to attosecond. So nanosecond is 10 to the minus 9 second basically, and attosecond is 10 to the minus 18 second. But mostly what kind of pulse laser you will see uh, in India or in any research laboratory is, that is the picosecond and femtosecond. So picosecond is basically 10 to the minus 12 second, and femtosecond is 10 to the minus 15 femtosecond, 15 second. So there are different procedure for generating this pulse laser, so that we will see in the next videos in the NPTEL courses itself. I am just mentioning these things. So the short time duration is a optional characteristic for laser. It is not necessary for the CW laser, but it is very necessary thing for pulse laser, because pulse laser, the pulse can be of any pulse width from nanosecond to attosecond. So there are method that is known as Q switching, mode locking, etc. So these are the method to generate the short pulses. So this method is not a fundamental property. It is specific to only some laser, but not for every type of laser. So considering all these property, there is one thing that we can say, that laser has a property that is very high directionality. That means that the laser beam will not spread as it will propagate through a medium. So by with con so considering this property, we can actually apply one process that is known as ray tracing. So ray tracing, so what do I mean by ray tracing? Here it is, here we will not consider this as a electromagnetic wave, we will just consider this as a ray. It is a just a straight line. Okay, so basically this is, again we are going back to the basic optics, that is known as geometrical optics. So in order to understand this ray tracing for laser, so if you have seen a laser beam in any lab or anywhere, or even for the laser pointer, you can see that the laser beam always goes like this. You can, like, for a uh, for other light sources it spread at its propagate through a medium, but for laser it is always like a straight line. So that's why we can treat the laser beam as a we treat the geometrical optics. Okay, so now from this what we'll do, so in order to calculate different aspect or different propagation of that laser beam or the light, we need to understand only need to answer only two questions. One, where is it with respect to some arbitrarily chosen axis, and two, in what direction is it heading. So only these two questions we need to answer in order to treat the laser beam as we treat EM wave in geometrical optics or in ray optics. So now suppose there is a dielectric medium of length d. So this is the chosen axis, and here this is the laser beam. Okay, so now, so first question is, where is it with respect to some arbitrarily chosen axis? So when the beam is entering a dielectric of length d, it was here r1. This is the distance from the axis, and the angle that made with the axis is theta 1 basically when it entered the dielectric, and when it exiting the dielectric, the distance is r2, and the angle it has made with the axis is theta 2. Okay, so one thing we need to assume here that we are talking about the laser, so this theta 1 theta 2 are all very small, so we can say that the tan theta equivalent to sine theta equal to theta. This is the approximation we can make here, because we are talking about a beam which has a high directionality. So now from here we can write r2 equal to 1 multiplied by r1 plus d r1 dash. And then r2 dash is equal to 0 r1 plus 1 r1 dash. So this r1 dash is basically theta 1 and r2 dash is theta 2. Basically these are the so I will just write like this: r1 dash equal to tan theta 1 equal to sine theta 1 equal to theta 1, and r2 dash equal to theta 2. So here, as this is not changing the direction when going through a dielectric medium, we can say that the r2 dash equal to 0 r1 plus 1 r1 dash, because the slope are equal when it is entering the dielectric and exiting the dielectric, and r2 is equal to 1 r1 plus d multiplied with the slope. So this is a two general very simple equation, and from that we can write r2 dash equal to 1 t 0 1 r1 dash. So now from this, the main point of using this matrix or writing this in the matrix form is that in general okay, there was some message or something. Yeah, Dr. Sadhana Sawant. Good evening, sir. I am not getting the link of previous recordings of problem solving sessions. Are they uploaded on NPTEL? Kindly send the link. Okay, so it was uploaded on the NPTEL as far as I know, because I have already sent the link. uh,
Sir?
hello, can you hear me?
Yes, sir. You have asked what,
Yeah,
sir, exactly?
so I have already sent the, I mean, PDFs to NPTEL basically. So if they have not,
Okay, but they are not uploaded yet, sir.
none of them, or is it just the
No,
PD?
nothing. We cannot see the, icon anywhere of problem solving session.
Okay, that's weird, because like we after every week's problem solving session, we generally upload the recording of this lecture and also the this notes. So
But
by
where is it? Is it on the whole the page where we are where we get
Sir,
the lecture videos and the assignment and the solutions?
where
Is it
can
on
we
the
find
same?
it, sir? Where can we find it?
okay,
In
that
the
I have to
assignment,
check, because the thing is that they have no, they have told me that they will send the link to the student. So I have not checked about it, that where it is uploaded or not. But from my
Can you
side,
okay.
can you please confirm and let us know, sir?
okay, I will just check with them and let you know
Because
in the
we
next
will
week.
make use of it now, sir. Because you
Sorry.
are teaching a lot, so we want to make use of it. It will be useful for us now, sir.
Okay, so that's a good thing. But okay, I will just check with them and let you know by next week. Okay, because I have weekly
Yeah.
classes. So and
Yeah,
Sure,
because we
sir,
have
sure.
missed, we may have missed some part, so we need to, see the videos or the lectures.
okay, okay. So I'll just check with them and let you know in the next class. Please join the next
Yes.
class. Okay.
Thank
And
you, sir.
if I get the permission, I will share the link with you guys.
Okay, thank you, sir. Thank you.
Yeah, welcome.
Sure, sir, sure, sir.
Okay, so this is the matrix for the transmission through a dielectric of length d. So we are using this matrices? So first of all, in general, the relation between the output and input parameters of a general optical system is given by a matrix. So R out, R dash out. So you always remember that R out is a position or the distance from the axis, and R out dash is the slope, that is this angle, or the tan theta 1, tan theta 1, tan theta 2. So basically R out dash is the tan theta 2. Okay, equal to a matrix A B C D R in dash. Okay, so this is the main idea of writing every propagation in terms of matrix, because for example, a beam is traveling in this direction and you put a block, then you put a lens, and then you put some kind of maybe mirror or something, anything you can put here. So what you need to do, that this light beam is input beam for this block. So let I just mark here 1 2 3. So the first medium, this beam is input beam, and then there is another beam that is, okay, I'll just use a different color. So then it is like this, and then this. Okay, so now for the first medium, this beam is this black beam is the input beam. Then what we need to do, we need to find the R in and R in dash. Then we'll calculate for this particular block, and we'll have the R out and R out dash here. Now for the second optical element or the lens, it will this R out and R out dash will be the R in and R in dash. Then again we will have this R out and R out dash here, and that will be used as the R in dash for this mirror. So basically what we need to do, we need to have we need to find the R out and R out dash, R out dash here. Okay, so we need to calculate R out and R out dash here. So in order to do that, here it is R in dash. Now we'll have a 2 cross 2 matrix for this block 1. Then we'll have another matrix for second optical element, that is the lens. Then we'll have an matrix for this mirror, and we need to have 3 matrix for 3 event, and we'll then just multiply everything 3 2 1 in the same order, the way the beam is propagating. So you will have that R out and R out dash. So by simply multiplying 3 matrix with the R in and R in dash, you will have R out and R out dash after these 3 optical elements. So that's why we need to understand this matrix method, so that you can easily calculate the position of the beam and the direction of the beam after going through some optical elements. And so this is the basic uh, advantage of using matrix method. Now in case of laser, why do we need this? Because as you know, the laser has a very high directionality. So in case of laser cavity, in uh, in the next week, or in the after the next 1 week, in the lecture videos or in course itself, you will be taught about the laser cavity and how the laser is generated actually. So there you will understand that this matrix method is actually used to understand the property of the cavity, because in laser cavity what is happening, there is this medium, and then the beam is continuously going through the medium and reflecting from one mirror to another. That's why it is actually amplified using a medium. Okay, so for this purpose I am just talking about this matrix method, so that when you come across the this cavity thing, you will understand why what is happening exactly. So in one line, the advantage of this ray tracing is ray tracing through a sequence of optical elements is reduced to simple 2 cross 2 matrix multiplication. So now I'll just this is the concept of matrix method. Now I'll just continue from here. So for instance, if we consider two lengths of dielectric, that is the so this is the axis. Now this is the laser beam or any kind of beam if you want to think, then you can assume. Then this is R3, D1, D2. So what I am doing here I am just showing two pieces of dielectric. One is D1 length and another is of length of D2. Now I will just write the matrix. So here you can see the R in is R1 and R out is the R2, but for D2 dielectric R in is the R2 and R out is the R3. So the way I have shown earlier, I can write it as R2 dash equal to 1 D1 1 1 R1 dash, then for R3 dash is 1 D2 0 1 R2 dash. So now what we will do, we will just write R3 dash equal to, so I'll just replace this R2 by this thing. So then we will write 1 D2 0 1 sorry 1 D1 0 1 R1 R1 dash. Okay, so now I will multiply these two matrix and we'll have R1 and R1 dash. So now So now if that dielectric has a refractive, so in general for transmission the matrix is only like this one dco1, but it will change to 1 d by n 0 1 if that dielectric has a refractive index of n. Now in case of a thin lens of focal length L, sorry, not L, F. So when you talk about thin lens, what do we mean? We mean that this lens is so thin that this distance is actually neglected in the calculation. Okay, so this is the assumption of thin lens. So that means that when a beam is going through a lens, we assume that no matter what the slope of the incoming ray and coming ray, the output position is always equal to the input position. That means that R2 will be always equal to R1. That is, if there is this kind of beam that is going here, then these two positions are always same. So this distance and this distance will always same. That is the R2 equal to R1. Okay, so as I have mentioned that this R2 R2 dash equal to A B C D R. Yeah, so for thin lens the R2 R2 dash equal, so for the metric method R2 R2 dash is equal to ABCD multiplied by R1 R1 dash. Okay, so now for thin lens R2 equal to R1, as we are assuming that the thickness of the lens is so small that the position of the beam at entering and exiting are same. So then what will happen, that is A will be 1 and B will be 0. Now consider the circumstances. So now if I draw the picture, this is a ray diagram for a thin lens. So this if are equal, but in my drawing it is not equal actually, but it is actually equal. So the input slope is here r1 equal to 0, because we are thinking that if we the way lens act is when we incident parallel beam on a lens like this one, the lens converges that beam to the its focal point, right? So when we are talking about the parallel beam, the r1 dash is equal to 0 because it is the input slope, and then r2 dash will be uh, so this is r2, so r2 dash will be minus r2 by f, which is equal to minus r1 by f. Okay, so r2 dash equal to r minus r1 by f, so that means that from the this here we can write that r2 dash equal to c r1 plus d r1 dash, and with comparing this we can write that c equal to minus 1 by f, d equal to 0. So that means for thick lens the matrix transmission matrix will be 1 0 minus 1 by f1. So for example, if there is a lens and then there is a block that is touching each other, then that means that two elements in cascade, then it will become 1 0 minus 1 f1. So basically the first thin lens has a focal length of f, and obviously the thin lens is converging lens, and then the second for the second element the transition will be 1 0 1. This will be 1 d minus 1 by f, 1 d by f. So this is the matrix transmission matrix for a combined transmission matrix for a lens and then a block. So the next component that is relevant for the component is mirror. So for mirror there is a problem, because when you think of a mirror, the beam is going like this and then it will come like this. So there is no input output, or you can say the input and the output is in the same side of the optical element. So for mirror, I'll just write the transmission matrix 1 minus 2 by r 0 1. So you can see that this matrix is actually similar with the transmission matrix of lens. Okay, so for in geometry, so the difference between the mirror and the lens is that the mirror, for particularly this mirror, this mirror is converging the beam at the same side of the entry beam, and for lens it converts the beam at the other side of the lens. That is the difference between mirror and lens. Otherwise, the mathematically or in geometrical optics, the effect of these two things is same. So basically what we are calculating here, we are calculating the position and the slope of the beam from the axis. So in order to obtain that, we can assume or we can see that the the effect of a concave mirror is same as a converging lens. And this r is the radius of curvature for this particular uh, concave mirror. Now what is the application of ray tracing? So the application of ray tracing is basically optical cavity. So one of the most important uses of ray tracing is in the analysis of optical cavities, such as the very simple but important one, that is the thing I have shown. So a beam entering and then it reflecting and then again reflecting like this and so on. So this is the effect of a optical cavity. So that is going, and here there is a medium that will amplify that beam. So due to these two concave mirror, the beam is repeatedly going through that gain medium and it is amplifying. Now the radius of curvature will be different for these two cavity. This one has R1 and this one is R2. R1 and R2. So now if we draw the equivalent uh, scenario for lens, that will mean that the ray is passing through lenses. Here one lens, then another lens, then another small lens, then another lens, then another small lens. So basically this lens 1 2 1. So though in my drawing the lens size of the lens are different, but assume that the size of this lens marked with 1 is same, and this is and the marked with 2 are also same. So there are basically two kind of lenses, 1 and 2. So when I'm saying this is reflecting from R2, it is actually going through 1, and when I'm talking about R1, this is going to through the second lens. So first reflection So this is first reflection, second reflection, third reflection, fourth reflection, fifth reflection, sixth reflection. So from here we can actually have a matrix for this 1 2 3 4 5 6. If there is a 6 bounds from the mirrors, then there will be 6 matrices, and then we will just multiply them like this: 5 4 3 2 1, and in this way we'll have the equivalent matrix for all the passes that is happening inside the optical cavity. So to analyze the stability of such a cavity, we construct an equivalent lens waveguide that would redirect the beam in same manner as the mirrors. Okay, so one thing I missed here is that it is also traveling a distance here. So this is the distance between the two mirrors. So this thing is d. Then we will have another matrix in between here. It will be of a d transmission matrix. So this will be the equivalence of the optical cavity. So now I will just calculate. So basically here what's happening, that here we are repeating this thing. From here it is going to d distance, then it is passing through the lens, then again it is going d distance, and then it is passing the another lens. So the if we define the unit cell, then it will have one transmission matrix for traveling d free space like this one, then this lens, then another d distance of free space, then another lens. So this is the unit cell that is continuously repeating. That means that the beam is the beam is traveling d distance and reflecting from the R2 mirror, then traveling another d distance, then reflecting from the R1 mirror. So this is the event that is repeating continuously. So in order to define the unit matrix, or sorry, the matrix for the unit cell, So computation of transmission matrix of the unit cell. So now you can see that the transmission matrix will consist of one transmission matrix for a for a free space of d length, then the matrix for a thin length of certain focal length or you can say a radius of curvature r or 2 here, and then focal length, then a transmitter for a free space of distance d, then again another thin length of curvature r1. So but here I will just write first with respect considering the focal length of the lens. So this is the first one. So here it is first the distance, then length, then distance, then length. So I'll just write from here. So I'll just use this one. So here it is a distance, then a length. It will be 1d minus 1 by f1, 1 minus d f1. This is for the first distance and the first length. D distance and first length, then again 1d minus 1 by f2, 1 minus d f2. This is the second d distance and second length. So now if we just multiply these two matrix, we will have a little bit big matrix, but this is still 2 by 2, 1 minus d by 1 minus d by f2, d plus d 1 minus d f by 2 minus 1 by f1 minus 1 by f2, 1 minus d f1, 1 minus d f1, 1 minus d f2 minus d f1. Okay. So this is the matrix for one unit cell of the optical cavity. But here we need to note that the main point of talking about the optical cavity is to find its stability, not to find the exact position or the exact slope. So from the in the matrix equation there are two variables or dependent or independent variable, that is r in out r in and r dash in, and then r dash out and r out. Okay, so from there we can actually eliminate the slope from this equation. So let's write those equation in a different way, that is rs plus 1 equal to a rs plus b rs dash. So this is after s number of transmission, this is the r out, and rs is the input beam for the s transmission or s event. Okay, now so then rs dash is 1 by b rs plus 1 minus a rs, and rs plus 1 equal to 1 by b rs plus 2 a rs plus 1 equal to c rs plus d rs dash. So here basically we have written the rs dash equal to 1 by b rs plus 1 minus a rs, and then we have used this, we have just increased the replace the s for s plus 1, and we have rewritten the equation. So rs plus 1 dash equal to 1 by b rs plus 2 minus a rs plus 1. Again this can be written in form of c rs plus d rs dash, because we write it like this, rs plus 1 rs plus 1 dash equal to a b c d rs plus 1, sorry, rs dash. Okay, so here this is the c rs d rs dash is this thing, and already I have written this one as this thing. So now rs, so from this equation rs dash 1 will just replace the value of rs dash, and we'll have rs, will have 1 by b rs plus 2 minus a rs plus 1 equal to c rs plus d by b rs plus 1 minus a rs. So now I'll just write rs plus 2 minus a rs plus 1, that will give b c rs plus d rs plus 1 minus a d rs, is you can so there is an important property of these matrices are this one, that when you take the determinant, so this is the abcd matrix. Now for abcd matrix, a equal to 1, b equal to d, c equal to 0, and d equal to 1. So when you take the determinant of this matrix, so what is the matrix, so when we take the determinant, we will have AD minus BC. Okay. Now if we think of this matrix, the determinant is 1D 0 1 is 1. So the determinant is always 1. Now if you calculate for this matrix, the determinant is again 1. Again for this matrix, the determinant is 1. The determinant is 1. So the property of this matrix is they have a unit determinant 1. So that means that AD minus BC equal to 1. So now applying this thing, we'll have RS plus 2 minus 2A plus D. We can rewrite the equation like this one, minus plus 1 plus RS equal to 0. So now in order to have a stable cavity, so what is stable cavity? Stable cavity means the beam is constantly reflecting from one surface to the another. So that means that this value of R should have a maximum value that does not cross the mirror. So if and by the value of R we mean that that is the race position. So if the race position is not bounded, it will eventually become so big that it will miss one of the component and thus walk off the mirror. So if the race position is so big that it will miss one of the component and thus walk off the mirror. So now if we constantly plot the value of R, this is the axis, then so this is the axis, and then I am just drawing the different position. So now so this is the R max and this is the unstable cavity and this is the stable cavity. So here you can see that this is the value of different R after the transmission. So for example, if I write this is s plus 2, s plus 3, s plus 1, s minus 1, s minus 2, s minus 3. So after after if each reflection from one of the mirror of the optical cavity, it is going to the value of r. So this is the rs minus 3 is here, then rs minus 2 is here, then rs minus 1 is here, then rs is here. So you can see for stable cavity it has a oscillating value and that does not go beyond the value r max. So all the rs is less than r max. But for unstable cavity the value is constantly increasing and at certain point it is going beyond r max. Okay, so this is the this is one of the very important concept of to understand the optical cavity that I have discussed today, that is the process known as ray tracing in geometrical optics. So here we need to answer only two questions, that is one is where is it with respect to some arbitrarily chosen axis and in what direction is it heading. So from that we, by using simple 2 cos 2 matrix, we can actually calculate the position of the beam after large number of reflection from the optical cavity, or you can say the round trip in the optical cavity. So by constructing this simple 2 cos 2 matrix for a certain event like transmission through a dielectric medium of distance d, or transmitting through a lens, or reflecting from a concave mirror which can be thought of a where we can thought of a equivalent lens transmission through a lens, then using those matrices we can actually have a application of this ray tracing in optical cavity, where in optical cavity the beam is constantly reflecting from one surface and going to the another surface and then reflecting from that surface and coming back to the previous surface, and it is so this repeated reflection can be thought of a transmission from two different focal length lens, which can be represented with this particular matrix, where we have, so this matrix actually shows the distance d, then length, then again d distance, then again length. So these four events are combined in this matrix, and if you calculate this, the determinant of this matrix is still 1, then there is a clever way to obtain the stability condition, and we just used as there are multiple reflection from the mirror in the optical cavity, we just cleverly use those equation where we have written the s plus 1th position in terms of the s position and s slope, and then we just replace that rs dash and we got the rs2 in terms of rs1 and rs. So from this equation we need to just find the maximum value of r, and if we know the maximum value of r, we can actually know the condition for which that cavity will act as a stable cavity or an unstable cavity. And in stable cavity the value of rs will never cross the value r max, but for unstable cavity it will grow and at some point it will cross r max and it will just walk off the mirror, and that cavity will not be cannot be used in laser. But in few cases unstable cavity is also required. So in the next class I will just find the condition for which the cavity will be stable. So here so this is for it for today's discussion. So in the next class I will discuss about the condition for which the cavity will be stable, and I will just show some problems regarding the ray tracing method, so that you can understand how the matrix method is actually used to calculate the position and the slope of the output beam after transmitting through a distance d, or transmitting through a lens, or reflecting from a mirror. So thank you guys for joining today's class. I'm ending the session.